Okay, so calculus. What is calculus? So when we're studying calculus, what we're doing is we're breaking from the static nature and getting into more of the dynamic nature. Back in pre-calculus, you're studying things such as slopes, how to solve for a particular equation, maybe doing some kind of plot, some kind of graph. Then when you get into calculus, calculus 1, that's where things really start moving. Literally, the things were moving, we looked at something called a limit. And what a limit is basically you're describing the behavior of a function as you're getting closer and closer to some particular value. So you might have looked at it from a graphical perspective. You maybe have some kind of location, or maybe x equals a. And you ask yourself, what would happen if I approach it from the left-hand side, and what would happen if I approach it from the right-hand side? And you really hit this hard for a while. You looked at limits in terms of a numerical perspective, you looked at it in terms of a graphical perspective, and then eventually you got into an algebraic perspective looking at limits. And for a while there, it's fine. If you were to take the limit as x approaches, let's say 2 of x squared plus 4x, well, you could graph this out. You could maybe factor out the x, and you would see it is going to be a parabola, intercept at 0 and at -4. And as you approach 2, you're going to approach it from the left-hand side and the right-hand side for the x values, which translates to approaching from the left on the graph and on the right on the graph to see exactly where that spot's going to be. And then whatever that spot is, the y value, that's going to be the limit that we call. And we had lots of different limit properties. And one of the properties here we have with this particular function is this function is a polynomial. And polynomials are continuous everywhere. So since it's continuous everywhere, we started just taking the 2 and we dropped it in. We did an evaluation. You might say 2 drops in, we get 4, then we get 8, and then we get a value of 12 for a limit. And for the longest time, that's how we think limits work. We think limits are nothing more than a plug and play until we get to a situation where we realize that's not at all what limits are, but that's what you think that they are. So you have to reprogram yourself to what it really is all about. If you were to take the limit as x squared minus 4 over x squared plus 5x plus 6 as x approaches the value of -2, if you took this and plugged it in, you're going to get that indeterminate form. You get 0 over 0. And then we have 0 over 0, we got to ask ourselves, okay, what does this mean? Because if I had something like a number over 0, I'm going to take a limit, I know exactly how this is going to play out. There's 3 situations. The first situation is this could grow without bounds. It can go towards positive infinity. The other situation is it could go towards negative infinity. And then it can also not exist. And whenever you're looking at a one-sided limit, that's what's going to happen each and every single time. One of these 2 different possibilities. And the one-sided, you might recall, is you are approaching from the left, you are going to be approaching from the right. And we designated that with a little superscript, so you're approaching it from the right, or we were approaching it from the left. And if we're talking about a 2-sided limit, that is talking about the limit that happens here and here. And if the limit goes to the exact same spot for my function, for the right and for the left, if r equals L, then we say the limit does exist, and that's where you have this whole entire x approaches a. Now, the thing is, if I have 0 over 0, it's a little bit different ballgame. I have to approach it a little bit differently. And one of the things that I could do here, since this is a polynomial, I can identify the problem. And that's what we're going to do throughout this course, is we're going to start identifying problems, because you can't solve a problem until you identify the problem. If you figure out what the problem is, then you can start developing some kind of plan, some kind of course of action to combat it and figure out the solution which will solve your given problem. Well, here the problem is I plug in this -2, I'm going to get 0. But why? You always want to take it deeper. Not that, okay, you do get 0, but why do you get 0? And the reason why you do get 0 here is because -2 is a root for the polynomial. In order for a particular value to be a root, you would take it, you would plug it, you would crank it, and then you're going to get 0. You're always going to root this down. You're always going to 0 it out right there on the x-axis. Hence the name root, hence the name 0. Well, the only way that -2 can be a root is if you have a factor in which you have x minus the root. That's always the case. And by understanding that it's x minus the root, this leads to a really interesting way of how to solve these problems that fast. Well, you can take this and you can factor it. And if I want to factor these, the problem is actually telling you exactly what to do. It's right there. It's x minus that root. And that's the only way you can get 0 out of it. Because when you plug in -2, do you get 0? Absolutely. So this tells you how to factor the problem without them telling you how to factor it. It's kind of a nice little trick right here. And then you just got to ask yourself, what else do I need where this is going to be x plus 2? What's the missing piece where I take 2, multiply it by something, get -4? And what do I need to multiply in order to get 6? And there it is. So that nice little trick makes this problem fall out very quickly. Then you would divide out the x plus 2's, get rid of the 0, and then you're left with this polynomial. And there's going to be no issue now, at least not at -2, in which you're going to have a point of discontinuity. The function will be continuous at -2, so it really is kind of a matter of plug and play now. You would take it, plug it in, and do your evaluation, and you do have your answer here in the very end. So you work these problems for a good long while, and then eventually you ran into another situation where, okay, you can't really do this anymore. You maybe ran into a situation where you looked at this, where you take the limit of sine of x over x as x approaches 0. Well, in this particular case, if I was to just take this, hit the big red button, plug it in, I'll have sine of 0, which is 0. If I plug it down here, I also do get 0. But I can't really use this trick anymore of factoring out the root, this factor. Eventually we got to something called L'Hopital's rule. Every Calculus 1 student's best friend, L'Hopital. And L'Hopital's rule, what it states here is, whenever I'm looking at the limit of f of x over g of x, as x approaches some value, maybe it's going to a finite value, maybe it's going towards positive infinity, but it's going to some particular value. What we're going to do here is if I have a particular situation, such as 0 over 0, infinity over infinity, L'Hopital's rule states if I'm looking at the ratio of the outputs on the function, I'm looking at the ratio of the derivative, the slope of the curve, the slope of the function, at that particular point. In L'Hopital's rule, it's a really great rule. Okay, so from here you would take the derivative up top, down below. You would have cosine of x over 1. And it made very short work of this problem now. Cosine is a continuous function, so cosine at 0 take it and drop it in, we do get 1. And we found this limit. And that was great, but there's more indeterminate forms than just infinity over infinity, 0 over 0. And another indeterminate form that we did encounter, if I take 0 and I times it by infinity, what happens? Well, when you first saw this, you said, well, I thought I was always taught 0 times anything is just going to be 0. Well, it depends upon the magnitude of the infinity. If the infinity has a stronger strength than the 0, then the infinity can actually take this and shoot off towards positive infinity. Or if this infinity doesn't have as near as much strength relative to what's happening here with the 0, this thing could send it off to 0 very quickly. And then we also looked at something like infinity minus infinity. You say, well, I thought infinity minus infinity is going to be 0. Well, maybe yes, maybe no. Think maybe like you have a rocket and you're trying to go off into outer space. Okay, that's my drawing skills. That's about all I have. But it's trying to shoot off. It's trying to escape the gravitational pull. Maybe the gravitational pull is pulling it down, and maybe the rocket's trying to escape. And if the rocket can escape being pulled down, this force there, then it can maybe go off into space. Or maybe the gravitational force is too strong. Maybe you're on Jupiter or something, and you're really trying to hit the thrusters, but nope, what you're going to do is become a pancake. That's crush. Maybe you do get back down to 0. Or maybe you have some kind of gravitational force where you're going to find some kind of equilibrium where you're never really going to escape and go off towards positive infinity, and you're not really going to go back down to 0, but you're somewhere in between. And we looked at a lot of different problems which were just like that. And another problem that we looked at is something maybe like 1 to the infinity, where we had 1 to the infinity. At first you said, well, that doesn't make any sense, because if I take 1 to the 20th power, I have 1 times 1 times 1 times 1 20 times, and I do get 1. And if I take 1 to the 100th power, I also get 1. So why is it then, when I look at 1 to the infinity, it's not really 1? Or could it be? Well, in short, weird things happen when we start venturing into the realm of the infinite. And our finite minds, our rules that we have, start breaking down. So we have to look at it from a different perspective. Suppose I'm taking the limit as x approaches positive infinity, 1 plus 1 over x raised to the x power. Well, whenever you're approaching a limit, what you do want to do is just push that big red button, cross your fingers, and hope nothing implodes. But the problem is, sometimes it will. Sometimes you will get one of these forms. And in order to use L'Hopital's rule, you can't use it here, you can't use it here, or here. It's only applicable for these two forms. So you got to figure out some way, somehow, to take this back to these two forms, to which then you can maneuver through the problem. Well, if I was to just let x go off towards positive infinity, this piece is going to go off towards 0. That piece is going to go off towards positive infinity. And what I do have is I do have that form. Well, the problem here is infinity. The infinity is an exponent. See, by identifying what the problem is, I'm starting to develop some kind of course of action, something I can do to combat this. I diagnosed it. Now I get to give it some medication, some remedy to overcome the problem. Well, whenever I see problems as being exponents, what I could do is ask myself, how do I contend with exponents? How can I take the exponent and make sure that it's not? I can use properties of logarithms. So if I take a natural log, I can use the property of natural logs to say if you power up the argument, that power comes out front. Now, if I was just to pause and stop the clock and analyze what's happening, and then start the clock again as x goes off towards positive infinity, I see that this piece goes off towards positive infinity. This piece still goes off to 0, and the natural log of 1 is 0. So now I have this form, where I have 0 times infinity. And when I encounter these situations where I have 0 times infinity, what I want to do, again, is get back to one of these two different forms. And I'm identifying the problem is I don't have that. I got part of it. So what I can do is take one of these pieces and just slip it down below. And the way that I can slip it down below is I can unsimplify the fraction. A lot of times we talk about simplifying. We don't always talk a lot about unsimplifying. But if you can tie your shoe, hopefully you can untie your shoe. I can't untie my boots. Literally, there's no shoelaces on my boots. So I guess I'm stuck. Oh well. So what we do is, a lot of times we talk about a keep change flip, where I have a fraction divided by a fraction, and we take it like such. But if I have this situation, there's nothing preventing me from going back in this direction. And that's exactly what I want to do. Now, if I start the clock again and say what happens as x goes off towards positive infinity, I'd see that this piece is going to be the natural log of 1, which is going to correspond to 0. And as x goes off towards positive infinity, when I look at the graph, because remember, limits describe the behavior of the function as you approach a particular value. As I approach positive infinity, the right-hand side is definitely going off towards 0. So now I do have the form of 0 over 0. And as soon as I have that form, L'Hopital's rule becomes valid. It's in play now. So L'Hopital's rule again is I want to take the derivative for the top function and then the bottom function. I'm not applying the quotient rule at all. I'm measuring the ratio, f over g, to the ratio of the slopes of the functions, f prime over g prime. So I'm going to take the limit of the natural log of y as x approaches positive infinity. I'm going to have the limit, natural log of 1 plus 1 over x over 1 over x. Now, if I looked at 1 over x, I can definitely do this a really complicated, really hard way. And the complicated way of going about this is, it is a quotient. I can definitely apply the quotient rule. But for me, if I can avoid the quotient rule, I'm going to, because it's long, it's complicated, it's difficult. And I don't like making problems more challenging, more complicated than they need to be. What I can do instead is use properties of exponents, recalibrate it, get a different perspective on the problem, and approach it from a much easier stance. Here, all I'm going to do is simply apply the power rule, where I take the negative 1, bring it out front, and I take its derivative. Take 1 off, minus 2. Now, this does lead us to the natural log. And you might recall, whenever you're taking the derivative for a natural log, you've got to be a little bit careful. This is a function composition. And whenever I see a function composition, I'm applying the chain rule. And the chain rule is stipulated if I have f composed with g, and I take its derivative, that's going to correspond to f prime g of x times g prime. And when I look at the chain rule as it's tailored towards the natural log, if I have the natural log of some function, let's call it u, here's what I'm going to do. I'm going to take u, I'm going to drop it, put it in the denominator, and up top, I put its derivative. And that right there is a chain rule for logs. And if I want to get the chain rule, let's say for each of the u, I would have each of the u times u prime. And we talked a lot about this back in Calculus 1, about these different chain rules. Well, in this case, I'm going to have the natural log of 1 plus 1 over x. And what I want to do is take the argument and drop it, and then multiply it by its derivative. So let's do that. I'll take the argument, I'll just drop it, and then the derivative of the argument, I want to make sure I multiply it up top. And if you note, that's 0. Because remember what a derivative does. A derivative measures the rate of change. How much change do you have with a constant? None. So the derivative of a constant is 0, because there is no change. But here I have the derivative of 1 over x. I already did that. And if I simplify it, I can take this piece, I can push it off. This is going to divide out. And if you like, there's your fraction again. Keep change, flip it. And as x goes off towards positive infinity, this piece right here tends to 0. That's my limit. But it's not the limit for the problem. We took the problem and we adjusted it, perturbed it a bit. That's the limit for the natural log of y. In order to go back to y, I have to release the y. I can do that by exponentiating both sides. And I use a property that exponentials and logarithms are inverse operators. They're inverse functions of one another. So the exponential e to the natural log, whose base is also e, shows us that we're going to get y here in the end, and that's my limit. So here I have a case where I have 1 to the infinity, and it's not 1. Rather, it's e. Now, this limit, we're going to come back to this limit a few times throughout the semester, so you might want to take note of it if you forgot how to work through this problem. And I can take this problem and I can calibrate this in a number of different ways. Instead of saying x goes off towards infinity, I could say, let's make x go off to 0. So I would change this 1 over x to x, and the x would change to 1 over x. And that's yet another version. It works exactly the same way as I go through the problem. And I can also take this problem and I can really start having some fun with it. Maybe I put a 4 right there and a 2 right there. And then the problem's going to change a little bit. But you're still going to have the same echo of this exponential e floating around. So the question is, if I start doing things like this, what's going to happen? That's something that the scientists, that's what we're all trying to learn how to be, whether it's in the computer science or chemistry science or engineering science. We're all plagued with the same thing of how things work and how can I do something and what's going to happen when I turn this dial and flip down that lever. Hopefully nothing implodes, but you're all kind of curious about certain things. Okay, anyways, so L'Hopital's rule is a really great rule. And then after we did L'Hopital's rule, we might have jumped into something like logarithmic differentiation, and then we really start looking maybe at rates, and look at something called rates of change, word problems, and then we did that for a while, and it felt like kind of like math hazing for a little bit, and then that was it, really. Later rates, no, we're not going to do too much of that here in this class. But looking at derivatives, we are going to be using certain properties of it. The derivatives like sine and cosine, we might run into that from time to time. Secant and tangent, we're going to run into that as well. Okay, so after we looked at limits, we did get into the idea of derivatives. And again, a derivative measures the rate of change. And this is something you see all throughout the business sector. marginal cost, marginal revenue. And you see it all throughout the engineering sector. It's just very, very useful, this idea of a derivative. And then eventually we got into something called integrals. And this is where we started looking at some things about the reversal of your derivatives. Now, whenever I'm taking a derivative of some particular function, derivative of sine of x, or the derivative of cosine of x, again, a derivative measures the rate of change. So if I was to look at the graph of sine and then cosine, well, what I see here is, looking at the slope of the function, that slope's positive, that slope's negative. Consequently, when I take a derivative of cosine, it's negative sine. And when I take a derivative for sine, it's positive cosine. And if I looked at the derivative, let's say of tangent, we might have remembered what tangent was, took its derivative, but we also might have forgotten. And if I've forgotten what the derivative for tangent is, and if all I ever did was just memorize my way through, I'm stuck. I can't go any further. But if I know how things work, when I run into a situation where my memory fails me, I can keep pushing through. I know that tangent is nothing more than sine over cosine. And I do see that this is a quotient. And because it is a quotient, I could definitely apply the quotient rule, where I'm going to take the denominator, I'll square it, and up top, I'll take the derivative of the function. So I'll have f over g again, f prime g minus f g prime g squared. I just want to follow that formula. Derivative for sine, that's cosine. But cosine times a cosine is a cosine squared. Then I'll subtract off, I'll have sine. And when I take the derivative from cosine, that's going to correspond to a negative sine. But there was one there to begin with. So that makes that a positive sine squared. And then we get to this, cosine squared plus sine squared, and that's where your spidey sense starts tingling. Because you're like, I've seen that before. The good old Pythagorean theorem. Cosine squared plus sine squared, that corresponds to 1. So the derivative for tangent is going to be 1 over cosine squared. But you can take this problem and you can tweak it just a little bit more by using the reciprocal identity for cosine, known as secant. Now, we can do this for all our different problems up here. We can also do this for our cotangent. And when I take the derivative of cotangent, what I'm going to come up with is a minus cosecant squared. And then likewise, I can do the same thing when looking at the derivative for secant. I can take secant, I could recalibrate it, I can re-express it as 1 over cosine. Then I can apply the quotient rule again. Derivative up top, derivative down below, square the denominator. And what we're going to see here in the very, very end is we're going to get a value of sine of x over cosine squared of x. but you might have seen it in a different way. You might have taken this cosine, broke it apart, and acknowledged that this is tangent and this is secant. And then likewise, you could have done exactly the same thing with your cosecant, but in this case what you're going to pick up is a negative cosecant. Pick up is a negative cosecant. Now, when you look at all these different problems, there's a nice pattern that's starting to come through. And mathematics, it's kind of a weird thing to say, math is not about calculations. What do you mean? I thought that's what we do. Well, we use calculations to help us to understand the problem. Math is really about logic, and it's about reasoning. It's about problem solving, critical thought processing skills. That's why, regardless of your major, whether it's an English major or early education, whatever it is, you're required to take a math class, because math is going to help you develop those skill sets of critically thinking through given problems. And one of the things that we're going to really look at throughout this course is pattern recognition, and also looking at certain issues, certain problems, and see if there's some kind of patterns that's going to be starting to come forth. And there's lots of patterns up here. And one of the patterns is this. When looking at sine and cosine, I'm just going to flip it and look at the reversal of it. Well, I see that pattern here also. I have secant and cosecant. It's like I take it and I just use the reversal of it, in a sense. And I see a pattern here that things are being squared when I look at the derivative for tangent and cotangent. So that's one of the patterns I do see. Another pattern is positive, 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 negative, negative, negative. And I see all the negatives occur whenever you start off with a C, C, C. So if I have my co-function, cosine, cosecant, cotangent, my co-function, when I take the derivative, I always pick up this negative. And that's something that I might want to remember. It's going to help me go into certain calculations when looking at these different trigonometric expressions. And after you did this for a while, looking at your trigonometric functions, we got into that idea of integration. In integration, it is the reversal of your differentiation. They're almost inverse operators. They're very, very close, but not quite. So if I know how to take the derivative, I can reconstruct the function that I want to take the integral of. So if I come over here and if I integrate left side and I integrate the right side, the integral is asking me for which function, if I take its derivative, do I get back to where I started. And the name that we have for this function is the integrand. So we take the integral f of x dx, capital F of x plus c. This part right here, this is known as the integrand. This part right here, this is known as your antiderivative. Here you have something called your integration constant. Your plus c. Please don't forget your plus c. And then this part right here, this is our variable of integration. And this part, it seems very insignificant. But this part can throw the problem if you forget about it. It's like a cornerstone where it seems so insignificant until you realize that's what's hinging everything together. This part is vital. This part right here is our integral symbol. And one of the relationships that we have here is if I take the derivative of my antiderivative, I'm back to where I started. So I can ask these kind of questions. If I take my derivative of my antiderivative, what's going to happen? Well, if I take the derivative here of my integral, I'm right back to sign because the integral of the derivative is like it goes away. Not quite, because there's a lot of different functions out there. If I take the derivative of sine of x, okay, yeah, I do get cosine, but what if I took the derivative of sine of x plus 1? I also get cosine. Or if I take the derivative of 5 pi plus sine, I take that derivative, I also get cosine. So I need to make sure I always tack on that ever elusive plus c, the thing that made you go from a 90 to an 89 in the class and you almost had your A because of that plus c. Gets you a little upset, I guess. And I did for a lot of different problems too. If I integrate a derivative, I'm back to where I started. And here, it's like that goes away. We'll say dx now to indicate that's the variable to which we're taking the integral of. And instead of saying the integral of negative sign, oftentimes we'll take it and just put it on top of the cosine. And then we definitely don't want to forget about that plus c. I can do this for all these different problems. So I'm looking at the integral of secant squared. I can ask myself, is there some function whose derivative is secant squared? And we do know one function. One such function is tangent. I take the derivative of tangent, I do get secant squared, and if I integrate a derivative, it goes back to the function. Using derivatives can help me in my integration process. Now, what we're going to do throughout this course is we're going to look at integrals and really hammer it and look at how we can go about the integration process. And some problems are going to be okay, and some problems are going to be a little bit less okay. And some problems will be like, oh my goodness, this is the hardest problem I've ever seen in my life. But you guys will make it through. Okay, well, that's about all the time we have here for today. I'll see you guys tomorrow. If you need anything, just let me know. You have a great day.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.